logarithmic. So let me remind you the three properties of the Kashaev quantum derivation function, which I'm going to put as a definition of a more general notion of a quantum derivation. So the function phi, just I recall it was a rather complicated spatial function, like this. Since B inverse Z minus phi x Z, and it has many different properties, but I would like to highlight three of them. So the first one is that it takes its values on the unit circle for any x in R. Second, it satisfies inversion relation in the sense that if I multiply phi b of x and minus x, this is some number independent of x but dependent on b, e pi I over x squared, not over, times any x in R. And the third property, most important, so operator 5-term relation, which tells that if I take Heisenberg operators P and Q and put them as arguments of the function, then I get unitary operators because of the property 1. And they satisfy this identity. P plus Q phi B. Everywhere sub B.
So doesn't I mean, you're taking the integral of R plus I epsilon.
Yes.
So epsilon doesn't play a role?
No, because this is holomorphic, but it has a pole at the origin.
Ah, so you need to move it.
You need to move it.
But if you take a different epsilon doesn't...
No, but Cauchy's theorem, in complex analysis, Cauchy's theorem tells us that you can deform contour, integral doesn't change.
Okay, all right.
Because the function is analytic. And here, so PQ are Heisenberg operators, so they satisfy this commutation relation, QP. So in physics, they write minus I h bar, where h bar is a Planck constant. But here I have special normalization. So in my case, h bar is fixed by inverse of 2 pi. But remember, here we have a parameter b, which is here supposed to be in to be a real number. And so the fact that h bar is fixed by inverse of 2 pi doesn't mean that I fixed Planck constant. I just moved it into b.
Mm-hmm. You change notation in the middle. You replace h with b, right? Somehow.
No. In reality, h will be b squared, something like it. So b will be square root of h bar actually when you try to relate them. But anyway, because this is a mathematics, we don't care where the physics is. So what we do care that we have a parameter. So we have a one parameter family of functions. And just to make contact with topology, which is behind our is the main motivation for all that, is that this 5-term relation underlies 2-3 partner move in triangulations. And in terms of mapping classbook representation, so it underlies the equation which we impose to T matrix, which is interpreted as a diagonal flip operation. And this inversion relation underlies a mixed relation between A operator and T operator, if you remember. And the A cube it doesn't show up because we throw away operator A because it is somehow comes granted as soon as we realize this. And what is my point? So, so this list comes just from this function as a properties. And now my main point is that these three properties I'm going to promote to a definition. But to make a definition, I should clarify what I will mean by PQ in more general context. And this general context will be self-dual LCA group. So let me just explain what it is. So we're contagion, self-dual LCA group. Okay, let me call it A. And so just as a remark, if we have a locally compact group, then there is a Haar measure, which is defined up to common normalization, which is a group invariant. In terms of abelian groups, so the Haar measure is translationally invariant. So it's left and right invariant. And then because of this Haar measure, we can now develop the Fourier theory. We define the dual group, which is as a set, which is a set of one-dimensional representations into unit circle, which are called characters. So a character of A is a map, is a continuous map chi, which goes from A to T. T, remember this is a unit complex numbers. Which has a group property. You preserve the group property chi of x times chi of y. And then, so the theory of locally compact groups tells us that the set of characters, so A hat, they're all characters, is an LCA group itself. So what is the product? So chi plus chi prime applied to x becomes chi of x times chi of x prime. Right. Sorry. So this is the group law in the set of characters, and it is abelian because complex numbers commute, and one can provide it with compact open topology. So with this topology, this becomes itself a locally compact abelian group. Then again, because of the local compacity, we have a Haar measure on the set of characters. So you can define its own dual. So you can consider double characters. And then this double dual group is naturally isomorphic to the initial group. And this is the Pontryagin duality. So this is reminiscent of the situation with finite dimensional vector spaces. We know that dual vector space is of the same dimension, and the double dual is naturally isomorphic to the initial vector space. This is not the case for finite infinite dimensions. In infinite dimensions, the double dual is a strictly bigger space than the initial space. And in that respect, so the locally compact abelian groups resemble very much finite dimensional vector spaces. And as we know, the most developed part of modern quantum topology is based on the category of finite dimensional vector spaces. I wonder if one can push it forward in the category of locally compact groups, using the Poincare duality as a substitute for the duality in vector spaces. This is just a remark. But my goal now is self-dual. So self-dual means that the dual of A is isomorphic to A itself. So this is self-dual. In that case, so there exists a F which sends A to A hat. So we can associate to any element of our group a character. And in this way we get an evaluation which maps a pair of group elements to a complex number of absolute value 1, and which is a group homomorphism with respect to each of the arguments. So this is why it is called bicharacter. Bicharacter. And so how it is defined? I am using this isomorphism. So f comma y in brackets is equal f of x applied to y. Right? F of x becomes a character, and character can be evaluated at x. And here I will now make an assumption. Assume that x, y is a coboundary. So any bicharacter is a cocycle. Right? If you look at the group cohomology, you write the differential, then the property that a function of two arguments is bicharacter implies that it is also a cocycle. So if I assume that this cocycle is coboundary, then it means that there exists a function. Let me call it just same letter with one argument. So this maps A to T such that x comma y equal x plus y divided by x and y. And what this I call Fourier kernel. Fourier kernel. And this I call Gaussian kernel. Gaussian exponential. I don't know if the isomorphism can always be chosen that the cocycle is trivial. This I don't know if it is a general fact, but all example I know of, this holds. So let us see now examples. So A equal R. Then xy becomes just e 2 pi I xy. And Gaussian exponential, this is the reason why I call them then Gaussian exponential. This is Fourier kernel, that's clear. E pi I x squared. So that's one example. Second example, yes. So that's we can take any A and take a direct sum with its dual. Then this is naturally self-dual, component-wise. Then chi x semicolon chi prime x prime. This is a character, this is an element of the group. Then the Fourier kernel becomes just chi evaluated at x prime times chi prime evaluated at x. And then what is the Gaussian exponential? It is just chi evaluated at x. So this is the second example. And in particular, if A equals Z, then A hat is T, and then Z N semicolon WM becomes Z to M WN. These are unit absolute value complex numbers. And for the Gaussian exponential, we have Z to N. This is just a special. This is a special case of this. When A is Z, then its dual is a unit circle, and then this is a complex number. This is an integer, another complex number, another integer. Then the Fourier kernel is this, and the Gaussian exponential is this. Okay, let me give more examples. 3. So A equal QP. This is periodic numbers, are the periodic completion of rationals. This is self-dual, and the Fourier kernel is given by E 2 pi I x y fractional part. Everybody knows fractional part of a periodic number?
Just to recall what is a periodic.
Yeah, periodic number is a series. So x can be written as a series p to, so p a prime, okay, prime number, and x is an infinite series sum over I from n up to infinity p power I xi, where the coefficients live in the finite set. So it is the analog of decimal writing of a real number. But the infinity goes with positive powers. So usually we write here 1 over 10 power I, right, xi, where xi takes values between 0 up to 9. And the series is convergent and so on and so forth. But in periodic numbers, 1 over 10 is replaced by p, a prime number. And so in periodic topology, this is convergent series. And it is better in the sense that when we add usual numbers, we start from the end, right? Which means that if it is infinite decimal writing, then we have to truncate, which means that we approximate our number by a rational number and then add. While in periodic numbers, you start adding from the beginning, so you don't need to truncate it. You can maintain arbitrary precision you want at any stage. So anyway, so this set of numbers has its own topology, and the fractional part is the writing up to only the negative powers. Sum I bigger than n, less or equal minus 1. So it is a rational number. Okay? This is a now rational number because the sum is finite, so the coefficients are integers, And so here you take exponential 2 pi I times this rational number. And this is a Fourier kernel of. And the Gaussian exponential is e 2 pi I x squared over 2 fractional part. Okay, so this is the periodic numbers, and you can go on. I don't know. There are infinitely many examples. And now I would like to explain what do I mean by Heisenberg operators now in the context of locally compact groups. Are you following me still?
At least majority of us have heard before this notion Heisenberg operator.
Okay, so but this is just a relatively simple thing. So we take L2 of L of R, so the space of square integrable functions on A, because we have Haar measure, and let me call a U operator is a unitary representation of A in L2 of A. That's by definition. So examples. Q. So it is A maps to unitary of L2 of A. And how I define it? So we have to define the Q of X. This should be a unitary operator in L2 of R. So I should be able to apply this to a function and evaluate it on Y. By definition, this is X, comma Y, f of Y. So it is a multiplication operator by this phase factor given by Fourier kernel. So I define Q by this in this general context. And in particular, it will correspond to this operator because remember that in the case of R, I have this Fourier kernel. So if I replace X by Q, I will have just unitary operators induced by position operator. And I define P operator of Y, which is given by translation, f of x plus y. And now you can check easily that Q, P hat of x, Q hat of y commutes like x comma y times Q hat of y, P hat of x. So that's what replaces Heisenberg commutation relation. Okay, and then we have to say what is the sum of two U operators. And in that case, the sum of P plus Q, but let me put it in quotation marks, it is a definition, right? So it is another U operator, is a U operator, in other terms, a unitary representation of A, defined by, so P hat plus Q hat, x applied to x, is given by Gaussian exponential power minus 1, P hat of x, Q hat of x. And if you and this formula is naturally generalizes the literal sum of P operators P and Q, because if we
so it's composition
the 2 pi I P x 2 pi I plus q x, you can check that this is equal e minus pi I x squared, e 2 pi I px, e 2 pi I qx. Yes?
You go quickly, so maybe you just slow down for a second.
Yeah.
So you start with locally compact abelian group A.
Yeah.
You consider
Self-zero. Self-zero.
Self-zero. Okay. You consider this algebra L2A of square integral function.
Yes. Not Hilbert space, not algebra.
It is not an algebra.
No.
So the product is not necessarily no.
No,
Okay,
no,
very
no.
good. So
It is
it
Hilbert
is
space.
just a Hilbert space.
Yes.
The Hilbert norm is an integral.
Yes.
All right. Now you consider unitary representations of your algebra A,
Of the group.
of the
A.
group A acting in this Hilbert space.
Yes.
For example, trivial representation, right?
It can be a trivial representation. This will be zero U operator. Yeah.
Okay. Now these U operators, you tell us how to add them.
Yes.
How to add them. Can you multiply them by numbers?
Yes. No problem. You just multiply the representation by a number. It will.
Is it still unitary?
Let me see. No, you can't.
You
You
can't.
can't.
So you can add them.
No. But you can add them. So you can make a group, a billion group out of them.
Is it a billion? Because this addition
Yes. This is a billion. So this is equal. But you should know how commute U operators.
because of this. Okay.
If they commute to some power here, you can add them. If you can put here any integer, and then you put here same integer.
Okay. Never mind.
Then they
Put
commute.
integer one.
Yeah.
So you can add these U operators. They form what? So they form a group. Or
They form a billion group.
they form
But the pairwise commutators should be integer power of the Fourier kernel. Only in that case you can add them. You cannot add arbitrary two U operators. You can only.
also, in your group A, you fix some Fourier kernel,
Yes.
and then starting from this Fourier kernel, you define some group, abelian group of U operators,
U of U operators.
which is in fact a set of actions of A in this L.
Yes.
Yes. Some actions. So some actions of A in L2A form an abelian group in some
Yes.
strange way.
Yes.
And what is your claim about that?
So, for example, if I take these two particular U operators, their sum is given by this formula, which generalizes usual sum of two Heisenberg operators. In the sense that I treat the unitary representations by exponentiated operators, and then this is algebraic identity, which can be checked.
Mm-hmm.
And this formula is not ad hoc. It just generalizes generalizes this particular case. And now I now arrived to a position when I can give the main definition of the lecture. What is a quantum algorithm over self-dual locally compact abelian group? So the main definition. A quantum algorithm over self-dual LCA group A is a function phi which goes from B to T, where B sits inside A of full measure. So the complement of B is negligible, of measure 0, such that, so the first relation, the phi of x, phi of minus x is equal some zeta Gaussian exponential. And second, pentagonal identity phi hat p, phi 2 hat equal, so sorry, I have to define what is a function of U operator. Sorry. But first I write the definition and then I explain what is a function of U operator. I thought that I prepared everything, but it happened. Okay, that's a definition. So instead of two properties, we have just three properties. We have one because now I just said that it is takes values in the units on the unit circle. And now what is a function of a U operator?
So p hat and q hat are those people in the example?
Yes, in the example, just this.
So you need the Fourier kernel from A.
Yeah, I need a Fourier, but I suppose, right, that I have Fourier kernel, yes. Good part. Where is the Fourier kernel? And Gaussian exponential. And so if we have a function on A or part of A, let me to be more. Let us pretend that B is just A. There are examples. You can think just complex numbers and A U operator. Then f of A is defined by this. F tilde of x, A hat of x dx integral, where f tilde is the inverse Fourier transform. Okay, so what you do, you take inverse Fourier transform of the initial function. You get, in general, some distribution. You have to, for example, if this is takes values on the unit circle, then it is in the distributional sense. You take the Fourier transform, and then you integrate with this unitary operator. With operator topology. So you get an operator. And in particular case, f of q is simple. It acts diagonally on the set of functions. L2 is just f of x multiplies g of x, for example. Because
why you write A hat on the right? I thought it was a representation.
no, A is an operator, right? It's a
Yes.
representation.
So A of x is a unitary operator in L2A.
Yes.
So you apply it to F tilde.
No. I weight it with f tilde and take a sum of unitary operators.
Okay. Okay.
So this is a scalar.
So what you get is what? It's an
Some
operator.
operator, maybe unbounded, whatever. It depends on the nature of the.
So that's F of A hat is an operator in L2A.
Yes. Maybe unbounded with some domain. And maybe not every way defined. And Yeah, so that's the definition. In particular case, when we specify A hat to be Q hat, then it acts diagonally. But P hat will be now more complex. So, and I'm using this definition for this phi in that context. So that's the main definition. And my message is that there are very many different examples.
Quantum delogarithm.
Of quantum delogarithm over different locally compact abelian groups. So let me just, yesterday I showed already one example.
So wait a second. There's the second condition. This phi of P hat is just a number, right?
No, it's a unitary operator.
Why it's written that phi is a map from B to T.
Yeah, this is usual function. Here is the usual function.
So
But now I insert operator argument here. It becomes operator in that sense.
so it's not phi, it's phi induced by phi.
Induced by phi.
So that's an operator.
That's the operator here. Everybody is in fact unitary operator because of this.
So your phi produces some operator, transforms this canonical P and Q into some other operators, and you want some condition of this operator.
Yeah.
Okay.
But this general scheme is just an attempt to generalize what we know about this Faddeev function. Actually, I mean, it doesn't come from nowhere. It comes just an attempt to axiomatize those properties. And the message is that it has other solutions. So, of course, first solution A is R, and phi is phi b of x. That's our initial example, the example which produced the definition. But let me now take A hat. Let me take A to be Z. And no, sorry, T plus Z, which is self-dual, with this standard Gaussian and the Fourier. Then phi of Zn is Z power maximum of M0. It is not easy exercise to check property 2, but property 1 is easy. Let us see property 2. So what we have to do, phi of Zn multiplied by phi of 1 over Z minus n. Right? This is the minus, this is multiplicative notation for complex numbers. So let us see what it gives. It's a Z maximum of n0 times Z minus 1 power maximum of minus n0. And you can convince yourself easily that this gives just Z power n, which is Gaussian exponential for that example. And the coefficient zeta in particular is 1 in this example. Let me give one more example of with the same group. this is more complicated example. Zn is equal fraction minus q 1 minus n z semicolon q squared infinity minus q n minus n z minus 1 q squared infinity, where q is real and absolute value real minus 0, absolute value of q is less than 1. So here I'm using the function infinite product 1 minus x, 1 minus qx, and so on. And you're using the fact that q is real, so the complex conjugate of the numerator is just the same function with z replaced by complex conjugate of z. So it is exactly denominator. So I'm dividing a complex number by its complex conjugate. So it is a pure phase. So this is a function which takes values on the unit circle. And so it is a quantum logarithm in the sense of that example, and it gives rise to quantum invariance. Quantum invariant, which is actually is known invariant under the name of Dimov-Guyot-Gukov tetrahedral index.
So this invariance of what?
No, just index of three manifolds. Which is with Garofalidis, well, it was also treated. And Garofalidis, Rubinstein, and their group, they proved the theorem that it is true topological invariant of three manifolds. And it counts just a particular case of the quantum logarithm over that locally compact abelian group. And for me, it is quite a surprise that it fits into this definition. So it can be this invariant. Usually, it is calculated with Neumann-Zagier data, okay, with Neumann-Zagier matrices, etc. And nobody described a local state sum or state integral definition. And now, with this identification, we just can apply the machinery of transforming this data to T operator, symmetrization with introducing dihedral angles, and then you get a local.
So for each time you have such phi, you have a three-manifold invariant?
No, unfortunately no, because you need some extra. For example, first example will not give an invariant. But second invariant has an extra symmetry property, which I'm not able to talk about now. Which gives so no, it is not always, but what is true, any solution of the system will give a unitary representation of the mapping class group, projective representations because of if this is non-trivial. Okay, my time is over. So I could continue, but I have to stop. Thank you. Yes, this is Dimov, Guyot, Gukov.
Those invariants, they are computable? Or
Computable, yes. I don't know how, but the invariants show up in the form of Q series. That a very interesting invariant, and the modular properties are open question.
Can they be used for distinguishing manifolds?
Presumably yes, but this is very new invariant. So it's I mean, all this subject, I just let me recall you that the underlying vector spaces cannot be finite dimensional. Yesterday I was highlighting this several times. So This is really outside of the usual machinery of quantum topological quantum field theory. So here if we arrive to invariance, then they are of novel nature, not finite dimensional. So we rarely have a polynomial invariance in this context. Typically they show up as special functions.